And we did like algae. We didn't get a chance to do coral because before that we were with Rich, and then we had to walk up the hill. So like we're just like missing out on all the other cool stuff because there's so much to do.
I was just saying, like you're getting lots of all the cool toys, and I get to see the messy labs.
No, I love that. No, 100%.
So we have two main projects here.
Hey guys,
Hey,
listen up.
Quick intro for so this is the Jaffe Lab. This is Devin. So like in marine sciences, there's so many different fields, right, that we can like use and work together on with different people. Yeah, we'll actually talk to you about that in a second. But basically, there's like geology, there's like marine bio, there's like chemistry in the ocean. There's also like engineering and developing tools. And we're kind of in a lab that Devin's going to talk to us more about. That's more on the engineering side of ocean sciences. So let's give it up for Devin. He's going to tell you everything about this lab and kind of what he does day to day.
All right, Devin.
So, thank you, Mo. We do a lot of instrument development here. So, a lot of engineering, trying to make low-cost instruments. These, yeah. So these are oceanographic floats, which is behind you have these nice big yellow housings. So you have a big pressure housing like this. This goes down to 200 meters. I would call it a marine robot, but it's kind of like the simplest robot. It only goes up and down really precisely, which sounds really kind of not cool. But scientifically, there's a lot to be discovered that way, right? We have a full CTD, so we can measure the density of the water, sound speed, all these different parameters, and you can actually track that. As to why you would do that, the question I would ask is, how do you measure waves? Right? You can do it with satellites. If it's on the surface, you can just go out there by hand, watch it with your eyes. But what about internal waves? Waves that are tens of meters beneath the surface. They're on like periods of tens of minutes. They're far too shallow, like far too quick to do with something like Argo, that you're getting like a GPS position a day. And you obviously can't really do that with satellite because it's 30, 40 meters beneath the surface. So what you do is you make really fancy glitter. Have you ever done that experiment where you put like two 2-liter bottles together and you make a tornado between them? You put glitter in, you can see all of the different vortices,
I could do it
right?
with one bottle.
You get with one bottle, yes, you can do it that way. You get the same, you get that little vortex. If you put a leaf on like a river going under a bridge, it's the same idea, but this case you're making it a lot bigger, goes much deeper, and you're tracking it acoustically. So, on the surface, you guys have used probably GPS on your phones. You can just use that to figure out where you are or where you've been. Anybody know how far GPS goes underwater?
We
use a radar.
Like this
Trick question.
You get this far underwater, your GPS signal's gone. You just can't localize. So what you do is you do acoustic beacons. So this is a really, really tall and bottom-heavy thing that is basically just a battery and an acoustic modem. So what that means is that you get a chirp. To us, it just sounds like a little click, like a whale click, but it's a slower chirp will go like, you just go through all these different frequencies. You get this very distinct signal. But you have 5 of these in an array, and because you know when they're going, you can then listen to your recording and figure out where you were inside that array. The math of that gets a little funky, but it's very similar to kind of echolocation, right? Where your bats bounce the sound off and they listen back, and based on the timing, they know where something is.
Oh, so that's GPS underwater?
Basically, yeah. It's the same principle, really, as GPS, where instead of to satellites, you're going to your buoys.
How about like sound underwater?
That's what these use. So, because GPS, most radio signals just don't go very far underwater. Sound is the opposite, right? It's a pressure wave. So you have sound that's going at 5 times as fast as it is in air, and it goes much further. So you can do a sound like this, and you can hear it audibly, clearly, several miles away. I realize that's a lot of random information.
No, that's all
Any
good.
questions about those, or?
So you want to measure this signal of the sound, so what are you trying to measure with the sound signal?
So that's a good point. I completely forgot that part of the context. I'm sorry. So these are designed as plankton mimics. So there's 2 things we're doing. We are trying, like I said, like that glitter, right? You're trying to make that glitter to observe these slow waves. But the reason we're trying to do that is because that affects a lot of plankton biology, right? You can have these slow waves, and just with moving your density, you can actually move towards the shore or away from the shore, right? You know, we go swimming, you're like, well, if I'm away from shore, I just swim towards it. But if you're a plankton, especially because zooplankton, you may not necessarily have like that ability. We may only be able to go up and down. And so something like just changing your density can allow you to move and bunch together. And so studying those dynamics are why we created these. Now I realize this is a lot bigger than a plankton, but we can kind of get away with it because the waves we're studying are so big, right? If you have things on periods of tens of minutes, these waves have wavelengths of hundreds of meters, maybe a kilometer. So on that scale, this is tiny, so it works.
That's true.
The other big project we have, there aren't any questions about that. We do a lot of imaging, so it's a fancy way of saying we put microscopes in the water and take millions and billions of images of plankton and then go, what do we do with this? Has anyone ever heard of marine snow?
What's marine snow?
That sounds cool.
Snow melted or?
That would be nice. I'll give you a hint, it's a lot grosser. Marine snow is just like dead plankton, plankton poop, whale poop.
Waste.
Yeah, everything from the upper water, little bits of soil and dust. You sneeze and you blow a snot rocket in the ocean, it becomes marine snow.
Remember detritus, everyone? Like the stuff that's on the seafloor, all that junk that some scavengers eat. That's like marine snow is like part of what eventually can make detritus on the seafloor too. But it's like the water column version of it. It's like earlier on.
Yeah, so it's coming from all the upper layers, and like Mo said, like that's actually a really important source of nutrients on the bottom floor and throughout the water depths. But you know, if you've ever gone gardening or your parents have gone gardening, you get diatomaceous earth. There's a good chance marine snow can also just become sediment. So this is also a great way to get carbon dioxide out of the atmosphere. Is study marine snow. Yeah.
What kind of scavengers eat the marine snow?
Oh, I'm not a biologist. That's a Mo question.
You know the answer to this. We talked about this on day one, right?
Yeah, some of those, I forgot the name, but they live in the deep sea.
Sure. I mean, you've got like sea stars too, right?
Yeah.
For example. Yeah, this is an example of sea cucumbers. But yeah, that's like the biology side of things. Devin talks more about like building tools to study like the ocean's physics and biology and ecosystems too, right?
It's a prank that interns did to us.
She has a lot of good questions now. She's
So yeah, throughout the water column too, bacteria will eat. It's called remineralization. They'll eat all this detritus and kind of put it back in the active carbon cycle. But there's a good chance it won't go in. The problem is we have no idea how much of any amount of marine snow, how fast is it sinking, how much is being reused, how much is sinking out, going as a sink. So we built this. I think the acronym is ATMARS, which I didn't come up with, but it stands for Autonomous Tracker of Marine Snow. So it looks very similar to our oceanographic floats, and it works very, very similarly, where you have a piston here. So this is just a buoyancy engine, which is a fancy way of saying you make yourself bigger or smaller like a pufferfish, and you can go up and down. But next to it is this nice PVC pipe of science here. Sorry. So as it goes down, we have side-lit. We side-light the marine snow and we image it as we're going. So in theory, we've tested it somewhat successfully. What you can do is then this follows a piece of marine snow, locks onto it, and just follows it down at the same speed down to a few hundred meters till eventually, it runs out and it goes and finds another piece. But that allows us to kind of track how much marine snow there is, how that's changing with depth, and how fast it's going. You had asked what this is. Well, with all these systems, you have to test it. That you have this great idea of what it's going to do of tracking marine snow, but then you build it and you discover it doesn't fit the way you built it, and you rebuild it about 10 times, and you test it with things like this. So this gives us beads of a known size, and because it's an acrylic, we can kind of suspend it and keep them in the same place. Right? You can imagine if you're trying to study particles, and you have just a water full of sand and you stir it up, it works great for like a minute, and then all the sand falls out and you have to keep stirring it up. So when we're calibrating, we like to have fixed known targets. It's kind of a general thing with engineering is you always start easy, because you always have this grand vision, but it takes lots of tiny little steps of, we want it to track marine snow, make sure it can actually see something snow-sized first that isn't moving before we try and watch it moving. Again, I am trying. I know it's a lot of information, but any questions about that?
Do you guys manually track the snow, or is there some kind of AI thing or some kind of computer program?
So it is computer vision. So if you look on here, you look in this giant mess of wires and batteries, we have an onboard computer. This is an NVIDIA Jetson. If any of you play computer games, I'm sure your computer probably has an NVIDIA graphics card. They also make these single board computers. Does anyone know what graphics cards are really good at besides games?
Mining.
Mining. This is for the same reason. It's lots of computation.
They use chips.
Yeah. That's why it's great for AI, because you can do lots and lots of parallel computations much faster than you could with a traditional CPU. Point being, for something like this where you're taking constant video and processing it, trying to say, oh, this is marine snow, this is something we want, this is not marine snow, this is a fish, don't try and track the thing that's actively swimming faster than you can go. All those decisions have to be made on here in real time. And hence why we have this beast of a computer, which may look small, but I think is about 99% of the power draw of this. So when they're both running, these have the same battery packs. On those, it can last for like 2 days. Here, it's like
1 hour.
4 or 5 hours. Yeah, it's sucking down the juice for that computer, but it works.
How much of this is fixed, and how much of it is actually moving up and down, and what's the range and motion for either of the parts, if at all?
So most of it is fixed. There's most of the housing.
Yeah, I guess. But then I guess, is the PVC tube of science also fixed, or is it moving up and down too, or
It is officially mounted to our housing with lovely cable ties.
Okay.
Oceanography is a dirty science, so we live off of electrical tape, hose clamps, and ties. But that is actually, we have just really large hose clamps that we mount this to the side. And then you have this steel or aluminum housing, pressure housing, and you're moving this little piston to make the whole thing, rise or fall. One thing you may note here is this top end cap looks a little different. So at the surface, we have to get these back somehow. You have an antenna, but like I said, GPS is only this far underwater. So you have to get the entire antenna really far out of water. So we just push the housing outside a little bit. This little piston will move probably you have a stroke this long, and it will make it rise or fall. But moving this just a centimeter gets the entire antenna out of the water with room to spare, so we can actually get it back.
So cool. So the track. Oh yeah, no, go for it.
So for the wave thing, do you guys just throw it in the water, and do you just look at the information on a computer, or do you swim with it?
Both. Generally, you don't swim with it unless something's gone wrong. Is the real answer? But there are many times where things go wrong, and you do end up swimming with it. But generally, for those that are going over the side of the boat because they're out for 12 hours, we would deploy them from I think you guys were to the pier, right? Mm-hmm. So I have my small boat cert, so I would actually boat us too. We've boated together before. Yep. So you launch down and we drive out. You would put a bunch of these out, and then you come back, hopefully at the end of their deployment. When they come back and they send you a message saying, we're here. I say hopefully because that doesn't always happen. Sometimes they just don't come back. Other times they come back too soon. All sorts of things can go wrong. But either way, you don't get that data unless we get it back. And part of that is just there's a lot of acoustic data on there. So if you think about, trying to send it's one thing to stream Spotify, but if you were trying to compress Spotify into a text message, that would be kind of difficult. That's kind of the amount of you're talking about all this acoustic data. Now you're trying to send it via text. It doesn't work very well. So we have to get it back to get all the data back. As for swimming with it, it does happen. Often when you go out over the side of the boat, I've had many times trying to scoop those out of the water where I was on the boat just by my feet, and the grad student was holding my ankles down, and if they had let go, I would have gone, whoop.
Oh my God.
But don't tell OSHA I said
Right?
that.
Yeah.
yeah.
We didn't hear that.
Yeah. yeah.
I thought you mainly attach these devices to buoys so you could see the currents and the sound of the ocean.
So that's another way to measure like velocity in waves, right? Like an ADCP, which is that's an acronym I should explain. So acoustic Doppler current profiler. So it's using sound waves, and you're measuring all the currents basically between you and the bottom. So if you think about like that same analogy of like the soda bottle vortex, if you imagine a big whirlpool. If you have a buoy on the side, just at one point, well, let's say it doesn't. Say it's a fixed buoy. What does that current look like? Right? It's just an arrow. At any point, you're just getting a little arrow. And so you won't know if it's the whole way, like you have a massive current, or if you have a whirlpool. So these are free floating specifically so that we can watch it go around in the circle. So that you can know it's actually moving with it. You can say, oh, the water is warmer here or something. And it is not me casting aspersions or denigrating buoys or fixed it. It's a different. There's
Fixed
strengths
buoys are
and
the
weaknesses.
worst.
Yeah. Fixed positions suck.
Free floating forever.
Yeah, take that, ships.
Yeah.
Does anyone want to ask one last question? Last question?
So we had interns prank us a couple years ago, and so at one point they came in and they hid 78 little plastic animals around the lab. So I mean, there's still like a rubber ducky up there.
Have you found them all yet, or you never know,
So
right?
occasionally I do find a new one, and I'm like, how long has this
Yeah.
been here?
Time
The
capsule.
rubber ducky up there I've known, but yeah, there's definitely been a few hidden in, like you open a drawer, you're like, whoa, there's an animal in here.
That's awesome. There's always fun in science, no matter what lab you're in, too.
That's
right?
awesome.
Yeah, at some point you can only stare at,
Yeah.
data points for so long before you start to go a little insane.
Yep.
Maybe 5 minutes.
Yeah. You're like, okay.
Fair enough.
And like I said, with engineering, it's always lots of small steps. So the amount of times we've spent a week on something that was supposed to be like an hour, and you're like, why isn't it working? And
Right. But it's a victory at the end.
yeah,
You
it's
get
a
it.
victory at the end. You
Feels so
realize,
good.
oh, I'm just bad at this, or I did something wrong.
Awesome. How are we on time right now?
We gotta go. Yeah.
All right, they're hungry. They're starving. I've been starving them all day.
A round of applause. Thanks so much
Thanks,
for.
Alan. Appreciate it.